All right, recording is live, so I better not fritter. So today is the second. It is September already. It's amazing. You will find today's lesson to be very simple, and I'm adding this on because this will take 10 minutes tops. And then after this, you can work on assignment 3 that I gave you last week, unless you're done. And then you can also work on assignment 4, which I'm about to give you. I would not be surprised if you walk out of here today with both of them completely done. There's not a lot of meat on either of those bones. Remember, assignment 3 was distance and midpoint, easy peasy. And then assignment 4 is what we're about to go over. So uh, in my standards, I am to teach you how to add and subtract complex numbers. And you might say to yourself, I think we already did that, Mr. Ahern, you're not paying attention. Well, I am to teach you how to add and subtract complex numbers graphically. Whenever I get to the thing about multiplication, I'm reminded every year that I don't think, unless I'm missing something from my past, I don't think I can teach you how to multiply complex numbers graphically until we do just a little bit of rudimentary trigonometry, because there's some sort of angular stuff in there that I think we need. So for now, we're going to keep it at what specifically is in the standards, and that is today, my mission is to teach you how to show adding and subtracting of complex numbers, but to do it on a graph. Got it? Okay. So in order to do this, you're eventually going to have a piece of graph paper. You don't need to worry about having it right now. But I'll just quickly show you how to do it. Might do 2 examples. Have you guys worked with vectors at all, like in Mr. Allen's class? Vector. Are you guys all familiar with vectors and how they work? Direction and magnitude, right? So our complex numbers feel a lot like vectors. And so when I explain this to you, understand that if this feels like we're talking about vectors, quite frankly, we are. I mean, full disclosure. So to show addition and subtraction of complex numbers on the plane really is to represent them as vectors and then do the, have you guys ever heard of the tip to tail method? Is that not a thing you do? I don't know what goes on in the building around me. So sorry, I need to pause this.
Perhaps fill my water.
No, not right now. Give me just a couple of minutes. I'll be fast. So here's a complex number. Let's do like 3 minus 6i. And this will be difficult for you as far as taking notes is concerned, but it's okay. And then let's add to it another complex number like negative 8 minus 2i. Got it? I happen to know for a fact that you could add those because you've already quizzed on it. You've already proven to me that you know it's essentially just combining like terms, right? So what your assignment is going to be today is you're going to do each problem twice. You're going to first graph the complex numbers and add them together graphically. And a complex number can essentially be represented by something that feels a lot like a vector. So what I should have done is color coded this. I wasn't thinking. So allow me a second. I'm going to switch and do, what was my second one, did I say? Thank you. So I'm going to do the purple one first. So this is a short lesson, but it doesn't mean that you want to ignore. So stay with me and here it goes. So to do 3 minus 6i, I'm going to go right 3, 1, 2, 3, down 6, 1, 2, 3, 4, 5, 6, and I'm going to mark the complex number right there. Now what I'm going to do is represent it with something that looks a lot like a vector. In science, when you want to add 2 vectors together, someone will teach you this. It's called the tip to tail method. So let me zoom in on this real quick. If this were did I resume my recording? Oh, good, I did. Yes. So I'm going to zoom in on this. If this were actually a vector, you would see this. This is called the tip of the vector. A vector is like a comet. The tail of the comet is in the back, the tip of it is in the front. And so what we're going to do now is we're going to apply to this using tip to tail method. We're going to apply the second complex number as a vector. So the second complex number is negative 8 minus 2i. So what we do is we leave from the tip of the purple vector and we create a new vector from that point. And so I'm going to go negative 8 minus 2i from where I'm moving my pen right here. That's what's the key, is we're building onto something from before. So I'm going to go left 8, 1, 2, 3, 4, 5, 6, 7, 8, and then down 2, and I'm going to wind up right here. And I am going to draw another vector like this. And what I found when I taught this last year was I was really happy about it because I got the sense that you'd never done this before. And again, I don't know what the science standards are. I don't know what science classes you've taken. I don't know what they look like. I know nothing about that. But I felt last year like what I was explaining to you wasn't just about complex numbers, but this is a really good, useful bit on vectors. And so, does anyone know how to calculate from that picture what the answer to the problem is? Yes, correct. And so what this is, I'm going to draw a third vector here. The red vector has a name, and I'm going to tell you what it's called. But the red vector is the answer to the problem. And in science, people would tell you the same thing. When you add two vectors together, this one right here is called the resultant vector. And the resultant vector is essentially the answer to the problem. So does it feel like overkill? It does. And if you feel at any point like, why would I do it this way? I don't want to hear about it. Just because I tend to some extent to agree that it doesn't seem contextually sensible to do with what we're working on, but it is a good excuse to practice with vectors. So the moral of the story is this, if you don't know where I'm going with this. What is the name of the red vector? In other words, this dot, that obnoxious red dot that I just made there, what is that complex number? Count it out for me, would you? I can zoom in for you here.
-5.
Negative 1, 2, 3, 4, 5, and down 1, 2, 3, 4, 5, 6, 7, 8. Can we agree it's -5 minus 8i? Good. So the goal for today's lesson is to get you to be able to add complex numbers graphically like we just did. And what did we say it was? -5 minus 8i? I didn't mean to put parentheses. My apologies. -5 minus 8i. The goal is on every single problem, you will do it graphically like this, and then you'll use your math skills to go back and actually math it. Pretend that we weren't talking about this graph stuff, and now just do what you would have done a week ago. And sure enough, if you were to add these complex numbers together old school, what is 3 plus -8? Jackpot. And what is -6i minus 2 more i's? Jackpot. The last thing I have to say about this is that I will also ask you to do subtraction with vectors. And subtraction as an operation in math doesn't really exist, for the record. We've lied to you for so many years about subtraction. Subtraction isn't a real operation. Subtraction is just an addition of a negative. And so we're going to do a problem with subtraction. So let's say, let me grab a graph, bring it in, get rid of that, and move this. And let's do a problem like, oh, let's do -4 plus 6i minus -10 plus 3i. So we get to connect old knowledge to new knowledge here today. And you'll remember that when the last unit, that last little quiz you took, what did we do with a minus sign like that? We distribute it, right? So your goal here, since you have to do this problem graphically, like when you take your next quiz, you're going to have to do these problems this way, whether you like it or not. And so what I'm going to watch you do is actually rewrite this problem not as a subtraction, but as an addition problem. So this is what the problem will actually look like. It's going to be -4 plus 6i plus, and what is the second complex number going to be? Good. And then from here, it's exactly what we would have expected. So let's do, I'll do purple first. So describe to me how to get to -4 plus 6i. Left 4, up 6. Perfect. So I'm going to go left 1, 2, 3, 4, up 1, 2, 3, 4, 5, 6. I like to mark it first and then bring my vector in. So there is the complex number -4 plus 6i. Got it? And then to the tip of that vector, we are going to attach the tail of a new vector, and I'll do this one again in green. From that tip, where do I go?
Right.
Right 10. Good. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Drop down 1, 2, 3. Remember, you are leaving from the tip of the prior vector. You are not resetting. That would, of course, defeat the whole purpose of trying to add these together. And then you're going to graph a new one like this. And do you guys remember what the red one is called? It's the resultant vector. Good. And I know we're not really doing vectors today, but I think it just feels like a real sweet time to talk about this nice sciencey concept. So the red vector represents the actual answer to the problem. And without even doing any of the math from before, just imagine someone just gave you the vector and said, count it. What is the complex number represented by red? 1, 2, 3, 4, 5, 6, 1, 2, 3. I couldn't agree more. So it is straight up 6 plus 3i, correct? Your job is always to substantiate or validate that answer by going back and mathing. Go back to the original problem in math. And it's really easy math. What's negative 4 plus 10? Jackpot. And then what is 6i plus negative 3i? Jackpot. You understand your task to calculate the sum graphically and then validate or verify the sum algebraically or arithmetically is more accurate there. Got it? So the rest of the day today, I'll keep the recording alive and I will just pause it. And then if you have any questions on assignment 3 from Thursday, let me know. Distance midpoint. If you have any questions on assignment 4, let me know. Otherwise, this might just be the end of the video if you don't ask any questions. Okay.